And I promise you yet another extremely interesting, informative, and educative session coming up right now, which is going to be on low resource adaptation of language and speech models. We have with us Professor Sunita Sarawagi, who's currently a professor in computer science and engineering department at IIT Bombay. And she's also the professor in charge of the Center of Machine Intelligence and Data Science at IITB. Her current research focuses on sequence models for text and time series, domain adaptation, effective human intervention in learning, graphical models, and structured learning. She is the recipient of the Infosys Science Foundation Award in Computer Science and Engineering, the Distinguished Alumni Award, IIT Kharagpur, and the H. Mathur Award for Excellence in Applied Sciences, all in 2019. She was awarded the PAKDD Most Influential Paper in 2019. She received the IBM Faculty Award twice in 2003 and 2008. Ladies and gentlemen, it is my deep pleasure to invite in front of all of you on the screen, the woman who leads from the front, Professor Sunita Sarawagi. Over to you, ma'am.
Thank you very much. Thank you very much. Let me see whether I can share my screen. Okay, good afternoon, everyone. I hope you can see my screen. So I'm going to be talking about low resource adaptation of language and speech models. So first we will focus on language models. Currently, it is established that massive multilingual language models are a very powerful method of transferring supervision from high resource languages such as English to low resource languages. So the central idea in these multilingual language models is that you first use unlabeled text from the various languages which may be of interest to you, and you train a multilingual model. So some state-of-the-art multilingual models are MBOT and XLM Roberta, and these models are trained with this masked language model objective in such a way that they are capable of taking as input a sentence in any language and represent them in some latent space which is shared across the languages. So essentially, you are disentangling the language from the meaning or the intent of a sentence. Now, this becomes like a very powerful tool for adaptation. So suppose now if you are interested in sort of using machine learning to solve NLP tasks like, say, named entity recognition, part of speech tagging, question answering, sentence entailment, and sentiment classification. Each of these tasks typically require lots of labeled data. But because we have this shared representation from these multilingual language models, you can do this kind of really surprising trick for transfer. You can just use labeled data in some high resource language. Let's say our high resource language is English. We use labeled data in that high resource language for your particular tasks. Let's say we are interested in named entity recognition. So we use labeled data for named entity recognition in English, and we use that to fine tune these MBOT models for the NER task. And surprisingly, such a model has been found to generalize quite well to other languages, even though it was fine-tuned only on English data. So the magic happens because we did this pre-training where we have co-embedded sentences in different languages in some shared space. So this is great when you have enough unlabeled data which you use for pre-training for the languages of interest to you. Now, we are going to be interested in scenarios where there are some languages which have such minimal representations on the web that even getting a decent amount of unlabeled text for training the language model becomes a crisis. For India, that is certainly the case. We have like more than 1,300 languages. And here you see the sizes of maybe the top 20 of these Indian languages. Compared on the y-axis, you have the number of Wikipedia articles, which you can think of as a crude approximation of the amount of digitized unlabeled text that exists for that language. So of course, English is totally out of the scale, and we have more than 6 million documents, Wikipedia documents in English. And if you look at the two most populous Indian languages in Urdu and Hindi, their sizes is 1/50th that of English. And if you consider any other language, say in this scale here, like Odia, the amount of text that you have for Odia on Wikipedia is almost 3 orders of magnitude less than that of English. And mind you, we are just talking about the top 20 languages, and we really would like to develop good AI-enabled tools for all, say, 1,300 plus languages that we have. So how do we achieve that? Now, of course, this problem of how do you come up with good language models for low resource languages is not a new problem in NLP. And many, many techniques have been proposed over the last 2 years. Here I am listing some prominent methods which have been developed, say, in the last 2 years. So one powerful idea was to increase the amount of sharing between any two languages by adding an additional alignment loss using parallel data in the two languages. So suppose if you want to make sure that the representation of a Hindi word is close to English sentences because you have labeled data, task-specific labeled data in English, then if you also additionally have parallel English and Hindi data, then you can impose an alignment loss so that related words in the two parallel sentences have similar embeddings in the two sentences. So this particular technique of adding an alignment loss using parallel data has been found much more useful than other ways of using parallel data, for example, which was proposed in XLMR. And we are going to revisit this technique in some of the work that we will be presenting next. Other ideas which have been proposed include designing, embedding adapter layers for specific languages, or maybe discovering shared tokens and anchoring on the shared tokens. But of course, the sort of the de facto technique is that you extend the word vocabulary with some more quota to handle your low resource language, and then you fine tune on the low resource language. And that currently is sort of the method of choice for adapting a language model, that's like embed kind of language model to a low resource language. Now, many of these techniques which are currently of focus in the ACL kind of conferences have been developed from the point of view of any two generic languages. So if you have English as a high resource language and you pick any arbitrary low resource language, all of these techniques would apply to these generic pairs of languages which you want to bring together so that you can do this transfer of supervision for any particular task. Our focus has been to see that if you pick languages which are more closely related, then can you do an even better job of co-embedding them. In particular, we were studying Indian languages because many groups of Indian languages come from the same family. So here, for example, we are showing a group of 6 languages which all belong to the Indo-Aryan language family. Now, there are 2 points of relatedness of languages within the same family. One, that even though on surface their script might look different, they come from the same family, say like the Brahmic script, where there is almost a one-to-one correspondence between the characters of languages in this family. And also, because these languages have co-evolved over several years together, they also share many common words. Now, if you leave the languages in their original script when you feed them to BERT, then the word overlap is lost. Whereas what we are going to propose to do is use the simple idea of transliterating to a related language to expose this overlap so that you bring the two languages even further together. A second dimension of similarity is of their sentence structure. Languages within the same family, they often exhibit common syntactic properties, such as they might have the same subject, object, verb order. Now, what's the outcome of such syntactic similarity? That it becomes easy to generate parallel data. Just now I discussed that if you have parallel data in two languages, then you can co-embed them even more successfully using techniques like the alignment laws. Now, if you have two related languages which follow the same subject, object, verb order, then generating pseudo translations become easy if you have a bilingual lexicon. Now, many of these languages have, traditionally, we have this culture of creating dictionaries to map, say, a word in Assamese to a word in Hindi. Now, if you have such lexicon available, we can get pretty decent quality parallel data just by doing a translation based on dictionary lookup. And this pseudo parallel data can be used along with the alignment laws to bring their embeddings even closer together. So we will see these two ideas in action in this model that we propose, which we call Relate-LM. So Relate-LM is a multilingual language model, which is specifically designed to exploit relatedness between a low web resource language and a related prominent language. So it may not be as high resource as say English, but it's a more prominent than the low resource language. So think, for example, language pairs like Punjabi and Hindi or Oriya and Hindi and so on and so forth. So our goal is that we will start with a pre-trained language model in that related prominent language, and we will use the limited amount of monolingual data in the low resource language and any available bilingual dictionary to adapt the pre-trained language model in the prominent language, but related prominent language to the low resource language. And this is what we are calling as the Relate-LM language model. So I'm going to go over the process of this adaptation in the next few slides. So the first thing that we do, as I was alluding to earlier, is transliteration. So since we have these languages which follow the same Brahmic script family, they are easy, they are easy to transliterate from one another by using simple rule-based systems. And in fact, a lot of such off-the-shelf rule-based transliteration systems exist between Indian languages. And also, since they have strong phylogenetic and geographical resemblance, this process of transliteration reveals a lot of overlapping words. Now, these overlapping words then can serve as anchors to co-embed even words which may not be the same across two languages by using the masked language model training, which is used in the MBOT kind of models. So let's go over an example. Say I have a sentence in Hindi, which is written in Devanagari, and I have a sentence in Punjabi, which is written in the Gurumukhi script. So most of us may not know this script, and so these two sentences look very different from each other. But if we use a transliteration library to transliterate this Gurumukhi script to Devanagari script, then we find that the Hindi and the Punjabi sentence, they look similar. And even if some of the words look like they are distortion of one another, there are in fact two words which are exactly the same. So even if we do no further pre-processing, now if I apply the masked language model laws on Hindi and on the transliterated Punjabi sentence simultaneously, then I am more likely to bring words like raha and riha together because they co-occur in similar context. So we did this small exercise of collecting statistics of the number of related words in, say, the prominent language which we choose as Hindi, and these three Indian languages, which we are assuming, let's say we are simulating them to be low resource languages, say Punjabi, Gujarati, and Bengali. Now, after transliteration, we find that each of these languages share like these many percentage of common words with Hindi. In contrast, if we transliterate each of these languages to English, which can be thought of as a distant prominent language, the number of overlapping tokens is much less. Now, the second trick that we are going to apply is a pseudo translation. So, as I mentioned earlier, it's easy to find bilingual dictionaries between languages. So, so many Indian languages, they share syntactic similarity. For example, they have the same subject, object, verb order. And because of that, we can generate pseudo translated sentence pairs simply by doing word by word translation. So we are going to just illustrate this with an example. Suppose if I have a Hindi sentence here, and I have a bilingual lexicon between Hindi and Punjabi, then each of these words of Hindi, I can pseudo translate to Punjabi just by looking up and replacing, say, this yaha Hindi word, which the translated word in Punjabi, whatever it is, we just type it over here. And now you compare the pseudo translated Punjabi sentence to the gold translation, and you find that they are quite similar, except for this one word for which there was no entry in the dictionary. So this pseudo translated parallel data is also quite good. Again, we compare the quality of the translation in terms of the blue score between Hindi and each of these three languages, and we find that the blue score is quite respectable, given that it was just generated by word translation from a lexicon compared to English, for which it is quite low. So once we have the pseudo parallel data, then when we pre-train the language model, we feed sentences in the two languages, and we impose an alignment loss between sentences, which we now know the words which are aligned across the two sentences because we generated them with a dictionary. And we impose a mean square error loss to reduce the Euclidean distance between embeddings of corresponding tokens in the two languages. So bringing all these things together, this is what the RelateLM pre-training looks like. So let's say we have in some low resource language, let's say again, we are continuing with the example of Punjabi, we have monolingual data DL, and we have this bilingual lexicon, which converts a word from the low resource language to the related high resource language. So this is Punjabi to Hindi dictionary. We have one bilingual lexicon. We also have a bilingual lexicon in the opposite direction from Hindi to Punjabi. And we have of course, monolingual data in the prominent language. In this case, it's Hindi. Now, the first thing that we do is transliteration. So we transliterate the monolingual Punjabi data to the prominent language Hindi, and likewise we transliterate the entries in the lexicon so that it's all in Devanagari. So now all Gurumukhi script has been transliterated to Devanagari, and then we do pseudo translation using the bilingual lexicon, and now we have converted, say, this Punjabi sentence into a pseudo-translated Hindi sentence, and likewise we have converted a Hindi sentence to a pseudo-translated Punjabi sentence. Now we are ready to do the MLM pre-training on the monolingual data, but this is the transliterated monolingual data, and between the pseudo-translated Hindi sentence and the original transliterated Punjabi sentence. So this is transliterated and this is pseudo-translated sentence. Between these two sentences, we impose an alignment loss between words which are related, and same thing we do on the Hindi side. And now these are very simple ideas, no major ML here, just simple, commonsensical data augmentation techniques. And we were embarrassed by the huge performance boost that we got out of these simple ideas. So first, let us look at the results of just adding to, just we will consider bilingual models. So our first experiment was that we started with English word, and to that we added, so we did MLM training with each of the 3 languages in their original script, and also we did that using transliteration to either English or Hindi. So when we did the transliteration to English, we started with word. When we did the transliteration to Hindi, we started with sort of a monolingual Hindi word. So the English word, mind you, is trained with 50 times more data than the Hindi word. Even so, if you just compare the eBird English and the eBird Hindi numbers, we find that for each of these 3 languages, if you consider task-specific accuracy for NER, part of speech tagging, and text classification, we find that this model here in this 3rd row provides much higher accuracy than the numbers in the 1st row. Now, on top of that, if we do transliteration, which is what you see in the 2nd row and in the 4th row, we get improvements, but the improvements are larger if you consider Hindi as the base model. Okay, and further, when we do also pseudo translation, when we augment with pseudo translated data, we get also very decent improvement in accuracy. Okay, so if you were to sort of compare like this last row over here with the 1st row over here, which is like the default way of doing things. Like you start with typically models which have been pre-trained with English because it has a lot of labeled resources in English. But then when you try to add any unrelated language to that model, you get much lower accuracy than if you started with a model which has been primed with a related language and you take additional efforts to bring the low resource language closer to the related language. So this was with bilingual models. Finally, we did experiments on MBOT. So MBOT did not have these 2 Indian languages, Odia and Assamese. So for each of these 2 languages, we did these 3 kinds of experiments. One is we just added that language to MBOT like you would normally do. And this is the accuracy that we get for Odia and Assamese for the 3 tasks of named entity recognition, part of speech tagging, and text classification. For Assamese, we did not have any test data, so this row is empty. In contrast, when we did the relate LM, but when we try to do relate LM with English as the prominent language, we got also some improvement, but not as much as when we used Hindi as the related language. And there, if you compare the 3rd row with the 1st row for Odia, likewise for Assamese, we find huge improvements. So one interesting thing to note is that for Assamese, so Assamese has the same script as Bengali. And Bengali is already present in MBOT. So when you transliterate Assamese sentences to English, you see a drop in accuracy here for text classification, because Assamese, if you just kept it in its original script, you would find that you get high accuracy because it already has some amount of Bengali data, which is kind of more related. In contrast, when you translated it to Hindi, then you get much better accuracy. Okay, so now the next question that we had is that suppose if you want to now add a new low resource language to BERT, to embed, then should you invest more in collecting unlabeled data for that language, or should you try to spend more time in collecting, creating a bilingual lexicon with, say, Hindi or the closest related high resource language that you can find? So these experiments were designed to answer that question. For each of these three languages, we compared the accuracy that we get with RelateLM kind of method, which depends on the bilingual lexicon and transliteration library, with just using vanilla BERT, but the dark blue lines denote increasing the available unlabeled data by a factor of 4. So if you compare the light blue line with the dark blue line, you see that, of course, if you increase the amount of unlabeled data, then your accuracy generally improves, but only by a small amount. And in most cases, the accuracy that we obtain with RelateLM is much higher than what you obtain with even 4 times as much unlabeled data when you do not take efforts to bring the LRL data close to some related prominent language. So as a summary of this part, what we have shown is that multilingual models are very promising as a tool for transferring supervision from high resource languages to low resource languages. But you can be more effective in that transfer if you exploit the relatedness among languages within a family. RelateLM was one effort in that direction, and we showed how the use of transliteration and pseudo translation along with alignment loss can give rise to more effective transfer. So one of the main conclusions from this study is that it's much better to use as pivot a related language than a distant language, even if that language has greater resource. And also it's more useful to invest in exploiting resources which bring out the relatedness between languages than in just blindly collecting more data. So this brings me to the end of the first part of my talk, where I was focusing on low resource training for language tasks. Now we are going to switch gears on to low resource adaptation techniques for automatic speech recognition. Now for speech, there are actually 2 dimensions of scarcity. One is the language dimension. So the accuracy with which you can do automatic speech recognition for English, which has a lot of labeled transcribed data, is much higher than you can do even for Hindi, which has significant lower labeled data, not to speak of languages like, say, Santali or Odia, which have significantly less labeled data. So the language dimension is obvious, but for speech, another subtle but very important dimension of differences comes out of differences in accent. So even if you're speaking the same language, say English, the differences in accent can give rise to huge difference in the accuracy that you can get of ASR based on what the model has been trained on. And when you talk about how to handle differences in language, the same kind of ideas that we have discussed for the language models, like training multilingual models, so you have shared representations. Such thoughts, parallel thoughts exist even in the speech community. Now, even here, there is effort for building large-scale multilingual models, so you have transfer across languages. But and also there have been techniques proposed for data augmentation. In fact, we recently did some work where we showed the effectiveness of transliteration for even ASR tasks. But these ideas do not work when we are talking about adapting to new or different accents. So in fact, this is just one small study that we did. We took, say, the ASR model, which was offered in Google Cloud, and by some very, very crude estimate, we thought that maybe it is trained for 50,000 hours. The actual number might be way off. This is just our guess sitting from academia. And we found that there is this Mozilla Common Voice dataset, which has like parallel sentences in English spoken by people from different regions. So if the same sentence, if it is uttered by English speakers, we obtained on this model a WER, word error rate, of 13%. But when we subset to utterances by speakers with an Indian accent, we got almost a 9% increase in WER. And with Australian accent, also we got like a 10% increase in WER. So which says that, accent mismatch is a big problem with, when we talk about, how to be fair and, provide similar accuracy across people in different regions. So even if we are only talking about, say, English ASR, we might be providing very different accuracies based on the accent. So what are the tools for accent adaptation? Again, this is also like much less explored than language adaptation, but even in this topic there is a lot of work. But we will be focusing on two specific tools. One is on model ensembling. So suppose if the labeled data for ASR is proprietary, then you will not have any opportunity for doing transfer at the data level. But let's say you have a trained model which you can access through an API, then how can you improve or adapt that trained service model to a local accent? So that is the problem that we will be discussing in the first part. Now, there are, of course, situations where you just absolutely must contain a little bit of labeled data for your target accent in order to, get any significant reduction in error rate. And in such cases, when you do have to collect labeled data, another interesting research problem is how can you actively collect such label data so that the amount of supervision required is minimized. So that is what I will be talking about in the second part. So first, let us talk about how we can adapt ASR model, which for accented speech, where the model is proprietary and it can be only accessed via an API. So it's a black box adaptation model. So here is the setup. So we assume that we have a server model which is sitting somewhere in the cloud, and it has been trained on huge amount of data, and it is available as a service, which means you can only feed it an audio sample and get back the text transcription. And you have the client, and let's say the client wants to adapt to Indian accent. And for the Indian accent, you have a small amount of label data. Say maybe we only have, say, 37 hours of English spoken with an Indian accent. Now, one thing you could do is, of course, there are a lot of open source tools say Deep Speech 2. This is when at the time that we did our work, this was Mozilla had this Deep Speech 2 open source ASR tool, and that already there is the Liberty Speech data. So we use that, and so that was like a pre-trained model for English spoken by say mainstream speakers, native speakers accent. And now using the Indian accent, limited amount of Indian accent data, we fine tune the model and we call that as our local or accent adapted ASR model. Now, even though the local model has been accent adapted, it may not necessarily be better or more accurate for Indian speech than the service, because the service model has been trained on significantly more amount of data. It has a stronger language model. It has seen more sort of noisy environment, more varied settings. And indeed, that is what we observed. We found that when we evaluated the service model on Indian accent, we got 22% WER, whereas even though we had fine-tuned the Deep Speech 2 model on the Indian accent, we got only 28% WER. So that seems depressing now, but the question is, can we do better? Can we somehow make use of this limited amount of Indian accent data to adapt this black box model? So one solution at the time that we thought about was alignment. So you take an input audio, say X, and you simultaneously send it to the local ASR model, which you have fine-tuned on the Indian accent, and the service ASR. Both of them will give you a sequence of words, and they will assign, say, a confidence attached with each decoded word. So C is the transcribed text from the local model, and Q is the word level confidence for that. Likewise, from the service, thus the output is S, and the confidence attached with each word is P. And now you can use an alignment algorithm. In the speech community, there are many libraries for alignment. One such well-known library is Rover. So you, for example, can take, say, suppose if there was a goal utterance, like everyone toasted the, and you submit this speech to the local ASR model, it did not get it right. It decoded it as everyone to state the, and these are the word level confidences attached with the decode. The service model also did not get it right. It converted the toasted to posted, and these are the confidences attached with the service output. And you feed these two sentences with their confidences to Rover, and it produces this merged output. Now the merged output is also wrong, right? And the reason, if you think about it, the problem is that, accent problems are often at a subword level. Like maybe an Indian speaker may not sort of roll the R's enough. So looking for word level merge from the two models can only take you that far. And maybe if you could do more fine-grained splicing, where you corrected the specific focused accent errors which appear in the speech of particular regions speakers, you could maybe be more effective. And that is what we tried to do. And so we thought that we need to do more fine-grained merging of the two models. So the next idea for fine-grained merging would be to do character level merging. And when we did character level merging in this data, we found that yes, it was indeed better than what we had earlier, but it was still failing in many cases. And one of the reasons was that the service model, it's a black box. It is not giving us character level confidences. It was only giving us word level confidences. So finally, we came up with this method, which we call fine merge, which uses an interesting way to do fine-grained alignment between the services output and the local model, which is the white box model. and it tries to kind of make up for the fact that the service is not giving us character level confidences. So the key idea is that we exploit white box access to the local model. So suppose we will just kind of quickly go through what the local model looks like, because this white box access is what we are going to exploit to do better splicing of the two models output. So here our local model was the CTC based model, which took as input a raw audio, and then it sort of, this was the CTC network, which was like a transformer kind of model, which output for each frame of the audio, it output a character distributions, which is what we're calling as the CTC output.
I'm sorry,
now,
Dr. Sunita,
yes.
we are very short of time. We've already reached the, we have some questions as well. Would you be open to take them, or would you want to just wrap up in some time?
I can take the questions, and that
Okay.
would also make it more meaningful. Yeah, sure.
Okay, yeah. Okay. Dr. Sarit?
Yes. Thank you, Anvit. Thank you, Professor Sunita. So there are some questions that that came up. I'll ask the first one. So the transliteration that you did is a sort of data augmentation. So other than transliteration, what are the other ways in which you can actually boost up the data set for a low resource language?
So, I mean, of course, I talked also about pseudo translation, and you could, maybe do, if there is some more work we are currently doing in terms of maybe doing tokenization differently, so that you can better expose the differences, the overlap among the different languages. So yeah, basically alignment losses, exploiting anchor words which are common. Parallel data, yeah, I don't know, there are a whole bunch of techniques. I discussed them. Yeah.
So related to this, so the anchor points that you talked about has some, let's say, have some words which are the same in the different languages, but they mean different. And so would that actually not pose a problem?
Yes, indeed, that would pose a problem. So we assume, like in many things with this embedding of, embedding learning research in deep learning, we sort of assume that such cases are much rarer. That in more cases, it's going to help you than it's going to hurt.
Right. So another question.
Yeah, so there is nothing, there is no good answer. These are all, sloppiness is rewarded when you have huge amounts of data.
Okay. So is there a way to use probably a weakly supervised method for data annotation? Probably it would work in a better way.
Yeah, that could be used. For example, we were also toying with these ideas. So even when you are doing, like, say, a dictionary lookup, there might be, when you look up, there might be many different senses of the word. So how do you pick the correct sense? These are all, so, these are the kind of things people used to worry about in classical NLP. And now it just sort of data trumps, and, somehow it's not rewarded anymore to think in a fine way, to make very careful distinctions, and thereby create a very complicated training logic, which cannot be easily vectorized. So, yeah, I mean, these are all fine questions and fine things to worry about. And somehow, again, maybe I'm kind of revealing part of my angst with deep learning, that sometimes just crude methods work better than more carefully designed methods. You can see that I have been burned by trying sort of more refined methods and them not working as well as crude methods.
Right. Thank you, Professor Sunita. Thank you. Over to you, Anvit.
Professor, if you could just maybe summarize the talk because we are really out of time.
Oh, okay, sure. Yeah. So basically what I wanted to say was that, okay, so then we have some method of doing fine-grained merging. So, you're welcome to look at this paper, and we get significant reduction in error by doing this fine-grained merging. And we feel that this is a very good way to do accent adaptation in the low resource setting. And now, of course, accent problems are at all levels. So what we talked about was country level accent mismatch. Now, the problem is even worse when you go one level lower and you look at accent mismatch within each regions, and there you have no option but to collect more label data. And we have some work on how you can sort of train a phoneme level classifier to find the hard sentences which will sort of bring out the sort of accents errors, which are often, we believe, at the phoneme level, to collect a more focused, useful label set for fine-tuning your ASR model. That is what this last part was supposed to indicate, and I'm going to skip through that. And now this is the last slide of my talk. So basically, we talked about 5 key points about how to handle low resourceness by latching onto high resource data sets. So one, of course, is learning shared representations. Second, we talked about how you can transform the LRL to bring it closer to the HRL. Third, you can do a whole bunch of data augmentation tricks. Fourth, you can try to do model ensembling, particularly when you're dealing with data which is proprietary. And fifth is that when you do need to collect label data, there is a bunch of work out there on how you could reduce the effort required to collect label data for your low resource setting. Thank you very much.
Thank you so much, Professor Sunita. I must tell you that this has truly been an enriching session in more ways than one. It was so educative, so insightful. So on behalf of the entire team, I would like to take this moment to thank you so much for your presence in the Very Large Data Engineering Summit 2021. Thank you, ma'am.
Welcome.